Good afternoon, good morning, good evening, everyone, wherever you find you in the world today. My name is Benjamin de Bucher, and I'm the head of events content for JEC Group. Thank you for joining us today. Today's webinar is Innovative Recycled PET Particle Foam for Waste-Free 3D Molding. Armacell's innovative range of the world's first particle foam based on 100% recycled PET offers solutions for waste-free molding of complex 3D shapes. ArmaPET Shape combines the outstanding mechanical properties of a structural foam core with the advantages of particle foam to create lightweight, strong, recyclable, and highly temperature-stable parts of nearly any shape. The portfolio upgrade makes it possible to mold at lower temperatures and to include inserts and metal parts directly in the molding phase. The webinar today will not only introduce you the product, but also suggest potential applications, possible molding processes, and after-use recycling of the molded parts. We will be hearing from Nadine WESSEL, Product Manager PET Foams at Armacell. Nadine is dedicated to the development of sustainable product solutions, providing enhanced value for customers. With an EMBA degree from the University of Münster in Germany in strategic marketing, Nadine is responsible for the global product management of the PET foams manufactured by Armacell. With several years of experience in different fields in the Armacell group, she has expertise in developing product solutions, focusing on responding to the market and customer-specific needs and optimizing internal processes. For almost 3 years now, the focus has been on the sustainable portfolio of thermoplastic core foams based on 100% post-consumer PET. We will be also talking to Dr. Sven Hendriks, Innovation Manager PET Foams at Armacell. Sven developed new innovative foam products based on recycled PET. He received a PhD in polymer engineering from Aachen University in 2017. He has a diploma degree in mechanical engineering, focusing on plastic and textile engineering. His previous research involved the development of foaming processes for bio-based materials, as well as fundamental research on foaming behavior and blowing agent solubility. So, do you want to know more about ArmaPET Shape particle foam and how it offers maximum design flexibility to produce lightweight, rigid 3D foam parts using an innovative fusion technology? This will be presented to you in the next 60 minutes. We will discover the benefit of ArmaPET Shape and how it contributes to a more circular economy. Quick reminder for our audience before we start, we will be taking questions at the end of this webinar as usual. You can ask your question in the question tab here on the right of your screen in the second tab next to the chat tab. I will be reminding you again during the webinar. You can start asking your questions from the beginning as it comes to your mind. You have also the possibility to upvote the questions from other participants if you find it interesting. In any case, the webinar is being recorded, so you will be able to view the entire program online later on gccomposites.tv, JEC Group Web TV. So let me now open the floor to Nadine WESSEL, Product Manager PET Foams at Armacell. Nadine, welcome online. Could you please give us the agenda of the webinar and a little bit of background on Armacell?
Yes, thank you, Benjamin. Gladly I will do. So welcome everyone to our webinar about the innovative recycled PET particle foam for waste-free 3D molding. I think Benjamin already gave a good introduction on what we will speak about today. So on the next slide, we have our agenda. So first we will start with a very small introduction about who we actually are. And then we will dedicate the time to speak about ArmaPET Shape. So a product overview, the topic on pre-expansion, processing, the specific product, which we call ArmaPET Shape H and its benefits, the general product range and the related mechanical properties, as well as the thermal resistance. And then the last part we will dedicate to introduce you to a recycling case study and also give you some insights on potential applications. Good. I will start with a few sentences on Armacell. So on the next slide, we have the introduction here. So Armacell itself is the global leader and inventor of flexible elastomeric foams for equipment insulation. So they traditionally come from the insulation area, but we have two main business divisions. So the advanced insulation and the engineered foams. This is where the PET is located for the composites business, which we will speak about today. Armacell has a headquarters in Luxembourg, and we do have regional headquarters everywhere for, and in total 3,200 approximately employees worldwide, working in 23 different production facilities in over 15 countries on 4 continents. We sell into various different markets, which also comes to the point that we are not only in the composite business, but also in the insulation area. And therefore, we are proud to say we are a multi-material and multi-product company. Moving to the next slide, we can see that we have a global presence with all the different manufacturing locations, as I just mentioned. The PET in specific, where we will speak about today, has the biggest manufacturing location in Themister in Belgium. You can see it over the Luxembourg, the green one. And then we have a facility in Brampton in Canada, as well as one in Suzhou, which is close to Shanghai in China, where we manufacture PET foam. Good, moving to the next slide. In general, in the PET business, we are proud to say that our approach is very circular. So we always start our thinking from really using material that is already on the market. So we start from PET bottles that are being processed into PET flakes. These flakes we use them as a base raw material for our in-house granulation to make PET granule, which is then used for the extrusion foaming of our boards and sheets, or also the particle foam. This is then being used in whatever application, and it's getting more and more that a lot of applications and customers are really focusing also on the very important 6th point here of this circle that you can see, which is the recyclability. So also these applications in the end, of course, depending on how they are being set up, can be recycled, and especially for the shape, we want to introduce it to you today, how you can have this full circular approach of using our ArmaPET products. Good. So in the next slide, in this context, we are very proud to say that until now we have used over 1.7 billion bottles in our production worldwide. You can see on the left side some equivalents, how this can relate into CO2 emissions. So in total, we speak about 76,800 metric tons of CO2 emissions, which would, for example, equal around 80,000 flights between Rome and New York one way, or 197,000 trips on the Route 66 with a motorbike, if you ever had the dream to do that in the US. Yes, so this is about our recycling background, and for us it's a really important story, and this is really in our DNA to develop products that are based on already recycled material and that can be put back in the circular economy later on. So on the next slide, I want to give you an overview on the product range that we actually have. So in general, we offer sustainable product solutions that enhance the efficiency throughout the manufacturing process and therefore also elevate the life cycle performance of the composite structure of you, so basically of our customers. Our traditional product here is the ArmaPET Struct, which is a versatile and durable solution for structural sandwich applications with a more environmentally responsible approach. So this is the traditional composite material, let's say, for structural applications, from wind turbines to trucks, basically everything in between where you want to have a lightweight but strong material. The ArmaPET Eco is the equivalent of this product, but in a direct extruded manner. So it's still a structural product, but less structural and has more focus on the insulation performance. So it has very good thermal capabilities to insulate products, so for refrigerated trucks, for example. The curve is designed for recyclable thermoformable microsandwich solutions produced in a continuous manufacturing process. So here we have really product and rolls so that they can be introduced in manufacturing, in continuous manufacturing processes, and they're very thin, so up to 3 millimeter for really micro sandwich applications. But what we want to focus on today is the ArmaPET Shape. And this is our particle foam that offers really the maximum design flexibility for any rigid 3D foam part using innovative fusion technology. And actually, yeah, that's what we want to speak about more in detail now. So moving on. Yes, so the ArmaPET Shape is actually the first recyclable PET particle foam, that is made from 100% recycled PET bottles. And it's basically our solution for cost-efficient production of 3D shaped structural foam parts. You can see some example pictures here in the middle, but we will come back to this. So moving to the next slide here. The benefits of a PET-based particle foam is that it has a zero waste approach. So instead of taking a block of material where you have to mill and cut, you can directly foam it inside the mold to the part size and form you need. In the specific context of the product we are introducing here, especially the Shape H, we also have integrated functions so that we can insert skins and insert already in the same process, in the same step, without adding additional materials. Therefore, we also have a superior production efficiency by reduced complexity by having all in one step. And in addition, it is a PET-based thermoplastic material, so we have outstanding thermal resistance, which we will show you in a bit more detail later on. In the context of CO2 emissions, you can see on the graph here in the middle that if we take the Shape as a baseline of 100%, a reference to a traditional particle foam like an EPS or also a PMI, as we see on the EPS, it's 166. PMI is even at 341% in terms of CO2 emissions. So also from the environmental perspective, we have quite some savings here. Good. So how is the value chain here? So basically, we start with the ArmaPET Shape production here at Armacell in Thimister in Belgium. We have our line to produce the particle foam. We can add on an optional coating, which is the Shape H version, which simplifies the molding process. And Sven will speak about this in more detail in the coming slides. One thing that is special and also different to some other particle foams is that in our case, we have an encapsulated blowing agents. And this means there is no need to have a separate preloading step with the blowing agent for expansion prior to molding again. So this is in the product and it stays in there. And at the moment, we can already offer a minimum shelf life of 1 year. The product is still quite new. Actually, it's in the industrialization to the market. And we're optimizing it further and therefore also hope to be maybe able to increase the shelf life even further in the coming years. For now, we're at 1 year, which is already quite great because it means you can put the material in your warehouse and still after several months, you can use it without another preloading. So in the next steps, it goes to the molding. And the coming slides will speak about this in far more detail. But there is also one thing that is an optional add-on step, which is a pre-expansion. This is something you can do to reach a certain density you would like to get. And this is now where Sven will take over and explain you a little bit in more detail how this can work.
Okay, thank you, Nadine. So I will start my part of the presentation with the pre-expansion of our ArmaPET Shape beads. So as Nadine mentioned, it is possible to further expand our beads starting from the bulk density after production. So in this example here, you see that we started with a bulk density of 280 grams per liter, which is one of our standard grades. And using an infrared oven that you see on the left side here, where the beads pass on a conveyor belt through this oven, it is possible to pre-expand the beads, and depending on the line speed and the settings of the infrared heaters, it is possible to achieve densities like 100 gram per liter or even 80 grams per liter, which is more or less the minimum density that we recommend for beads that should also be molded in the next step.
Sven, I have a quick question on this slide. Sorry to interrupt. Will the final expansion of the beads be limited after pre-expansion?
Well, so if you would expand them too far, so below 80 grams per liter, then at some point they can't expand really further. But within the ranges that we have tested, you need to respect a certain quarantine time of several days after the pre-expansion step. And this allows for the gas exchange and the increase of pressure in the beads, and then the expansion for the final molding step is still sufficient.
Okay, thank you, Sven. I want to remind the audience that you can also ask your question in the question tab, and that we will answer them at the end of the webinar.
Okay, so I would like to go on with going in detail about the molding processes. And before covering different methods how to mold it, I would like to describe the molding process in general. So after filling the mold, the second step will be always the heating of the mold and expansion of the beads due to the introduction of heat, and it will also generate a certain pressure within the mold to really fill all the gaps. An optional step that can be done is the compression of the material. So by further closing the mold, we have found that 10% compression will improve the fusion and part definition. And following, the third step is the fusion of the part at high temperatures. So for our standard shape P grade, the molding temperature should be around 230 degrees. And for our surface functionalized shape H, the molding temperature needs to be around 180 degrees. Then after fusion, you need to cool down the mold and the part rapidly before demolding it in the last step. And the typical demolding temperatures are around 80 to 120 degrees C, depending on the molding method and the part geometry. And the full fusion strength will develop after the full cooling of the part. So after, like 1 hour after molding. Now I would like to introduce different molding methods in terms of machinery that can be used for our particle foam beads. The most straightforward method is maybe using a heated press or a heated mold. This is also the technology that we use together with our partner Swiss CMT when developing the coated beads grade, and it's simply using conductive heating of the mold by a heated press or maybe a heated mold. A second technology is steam chest molding, which is known as the common method to mold EPP or EPS parts. Here you need, of course, a very high temperature to fuse the PET beads. So you also need high pressure steam systems. For example, the Institute Neue Materialien Bayreuth, they have such a machine that we also tested to fuse the PET beads. Another technology that is available in the market for a couple of years now is radio frequency molding, developed by Kurz Ersa. This technology uses a high voltage electromagnetic field, and similar to a domestic microwave oven, the energy is absorbed in the molecular structure of the particle foam. On the following slides, I will describe the heat transfer methods that are corresponding to the molding methods. Using a heated press or mold, the heat is generated by heating oil or by electric heating elements, and the heat transfer into the part is pure conduction of heat through the press and the mold. On the other hand, for steam chest molding, the heat is generated by heating water to produce a high pressure, high temperature saturated steam, and this steam is passed through the particle foam beads inside the mold, and the heat will be transferred from the steam to the beads. So this method is also suitable to mold parts with the higher thickness, because you can introduce the heat into the core. Similarly, for RF molding, the heat is generated by the absorption of the electromagnetic field in the material. This also has the benefit that the part is heated internally, and it can also work for rather high thickness parts. Another aspect of molding is the variothermal processing that we recommend to use for our beads. For the heated press, it is applicable for the cooling of the part. So an additional oil or water circuit to cool down the part rapidly will shorten the cycle times. For steam chest molding, it is also a common practice to inject water into the steam chamber to cool down the part after fusion. On the other hand, for radio frequency molding, additional oil heating of the mold can improve the surface quality of the part and will also help for further cooling of the part if switched to a cooling circuit of oil, for example. Coming to the next slide, I would like to go in more detail about the molding with the heated mold. In this case, we used a mold with oil as a heating fluid, and the mold was operated using a servo press. So the cooling circuit of oil runs at 70 degrees C, while the heating circuit runs at 250 degrees C. In the first step, the mold is filled with 110% of the final volume of the part, and then it's closed partially to allow for some expansion of the beads while heating them to 200 degrees C. Then in the third step, the mold was fully closed and further heated to 240 degrees C. And afterwards, after the full fusion, switching to the oil circuit of 70 degrees C, the part was cooled down rapidly and then demolded at a temperature of around 110 degrees C. And finally, the mold will be cooled down again before filling it for the next cycle. And such process has the best efficiency for part thickness below 15 millimeter in terms of cycle time, and the mold and press technology is widely available on the market. On this slide, you will see some details about the RF molding process, which is, as said before, using a high voltage electromagnetic field that is absorbed by the molecular structure of the beads. And here it is also combined with a variothermal oil heating. In the first step, the beads are filled in the cold mold. Then the mold is, in this case, it was closed fully, so the beads were slightly compressed while they were still cold. Afterwards, the beads are heated using the internal RF field, and also heated with oil around 190 to 210 degrees C to improve the surface finish. Then you cool down the part, and finally you can demold it as described already before. For this process, the benefit is that there's rather no limitation of the part thickness because the heat is generated inside the part. However, this technology is still quite new, and the mold technology requires, for example, the simulation of the RF field, because you also have to consider the reaction of the mold material to the RF field, and also some specific aspects regarding the geometry.
Quick question again for you, Sven. You just presented different molding methods. Which method would be suited for which size of series to be produced?
Well, that pretty much depends, yeah, as you mentioned, on the size of the series. So for small series parts, I would say that it's probably easiest to do with a heated mold, because the technology is available and the manufacture of the mold is quite straightforward. When you would like to produce a higher thickness part in very large series, then it's probably easier to go for the radio frequency molding, because yeah, that could have then the benefits regarding cycle times.
Thank you, Sven.
Okay, as mentioned before, we have developed a new surface functionalized grade of our beads called ArmaPET Shape H, which we have developed together with our partner Swiss CMT. And the main benefit of this material is that the fusion and curing can already be done at lower temperatures, so starting from 170 degrees C, or going also in the range of 180 to 200 degrees C for better cycle times. So it can be molded at lower temperatures. It has an improved part definition, since it is already expanding very fast and also at low heating rates. And because of the fast expansion and the lower temperatures, also parts with higher thickness can, for example, easily be cured in a mold which is put into an oven. And also the mold can be quite simple then, so it mainly needs to withstand the certain temperatures, and you need to apply, for example, a PTFE foil or mold release for easy demolding of the part. And the second main benefit is that this grade also provides a very good adhesion to skins and inserts without using any additional adhesive. And here you are quite flexible in the selection of inserts, since it will bond to most common materials, also including, for example, alu, steel, or common plastics.
Sven,
yeah.
Sorry, Sven, I have a question on this
Yes,
point.
sure.
What needs to be done to prepare inserts for molding?
Well, as you see in the pictures here, there was mainly no preparation for the inserts. So, for example, for the part that you see on the bottom, the insert was just put inside the mold. I think here there was also some skin put into the mold, and then the mold was, so it was molded like upside down, and then it was just filled with the coated beads and molded using a heated press. So mainly there's no preparation needed for the inserts, as it will directly bond to the coated Shape H material.
Thank you.
Okay, you're welcome. Finally, the parts that you make, they also have a improved durability So we saw no degradation of the mechanical properties, even after 3 weeks exposure to elevated temperatures at 150 degrees C. And of course, the material, due to the nature of PET, it will soften at high temperatures, but we still observe the full integrity of the part, so without having a load applied to it. The processing of ArmaPET Shape is similar as for the Shape P. In this case, it's just that you need lower temperatures. You also overfill slightly the mold to achieve some compression. It's also possible to not fully close the mold in the first step to allow for some expansion while heating the material to around 140 degrees C. And there we recommend a short plateau to allow the full expansion before compressing the part to the final thickness, and then to allow for the curing between 170 and 210 degree, and depending on the temperature that you can achieve with your oven or mold, and also the temperature that you reach in the core of the part, you can see from this curing graph the time that is needed to achieve a certain level of curing. Finally, for cooling down, if possible, you can also use a variothermal process to cool down rapidly, or if you have a mold that you just put in the oven, then it can be simply cooled down outside before demolding it. So now I will hand over again to Nadine to guide you through our product range of ArmaPET Shape.
Yes, perfect. So thank you, Sven. Sven gave us a good overview of what can we actually do to get a molded piece. And during that part, he mentioned a few times ArmaPET Shape H or pure beads, etc. So this slide here is to give you an overview of the product range of what we have available. So basically, we speak about two different shape versions. So the Shape P, which is the standalone PET beads without any surface functionalization, or also called coating. And we have the ArmaPET Shape H, which is a specifically developed grade, which has been optimized together with this specific coating to ease the molding. So we spoke about it. You have less temperature. You can directly insert metal parts, skins, etc. You don't need any additional resin, no additional step to really make it easy. So the Shape P comes in two different densities. So here we speak about the bulk density. That's important to say. And we speak about 200 and 280 grams per liter. The bead size is around 3 millimeters. So that's a nominal bead size with some slight tolerance up and down. And then in the third row, you can see what the final part density can be. So if we do not have a pre-expansion step, as we recommend for the 200 gram per liter, and this is valid for the Shape P and the Shape H, we will end up with a final part density of roughly the same as the bulk density, slightly higher because we recommend the overfilling to get a proper part integrity and surface. The 280 gram per liter is the one that we recommend pre-expansion for if needed. So normally the pre-expansion is not a mandatory step, but in case a lower density is needed, we recommend to start with the high density beads, even though it's a little bit counterintuitive in the beginning. But this is the grade you can basically pre-expand to start with a density of 80. In the last row, you can also see for which kind of processes we recommend them. So for the Shape P, we recommend them for the radio frequency or an oil heating press or steam process where you can reach the temperatures above 230. But as we know, this is quite challenging and not standard in a lot of processes. We have put a lot of effort together with CMT, and thank you again, Marcel for this, is the shape H. So basically also the 200 grams per liter. It's, as I said, a special grade, but comparable to the shape P with this additional surface functionalization. And there you can mold it from temperatures between 160 to 200 degrees Celsius, as Sven just presented on the slide, the diagram with the different residence time per temperature. Good. Moving to the next slide, we would like to also show you here a reference value, and it's important to say these are just typical values for some molded parts that we internally molded in a heat press process, how the mechanical integrity of a final part looks like. We have to say that this will of course depend and vary on the part size and the molding method that you have. So this is not like a granted value that we can guarantee, but just to give you a reference on how the product will behave in terms of the compression of the shear, shear elongation, and also the compression modulus at elevated temperature. One special thing you can see here, so from the density you see there was this effect with the overfilling, so the shape P200 and H200 both had a part size density of around 220. And who has a sharp eye and has already screened the values sees that both 200 gram per liter grades on P and H both have the same values. And that's an important message from us to you, that basically the coating is really designed to not change your final part, but really to make it easier to mold it, to make it very more convenient, more accessible to all the methods that are available on the market, to reach a final part that is comparable to the one without the coating, but just making your life easier here. Good. Moving to the next slide then. So we already spoke about having a high temperature resistance here. And this picture is here to illustrate in comparison to the EPS and EPP together with the ArmaPET Shape. So we had 3 samples and they were all put in an oven at the different temperatures you can see at the left for 30 minutes. And you can see at room temperature, of course, they all maintain their integrity. At 140, the EPS is already molten and the EPP is starting to degrade. At 160, also the EPP has suffered quite a lot. And at 180 degrees, both of the competitive materials have been molten, while the ArmaPET Shape still fully maintains its integrity. It softens, yes, but it doesn't lose its shape. And basically, we have also tested then further values at elevated temperature. So Sven, moving to the next slide. So when we tested really at elevated temperature, so this was an external test with the laboratory where we have really asked to measure it at elevated temperature, you can see that we still maintain integrity. Of course, the compression strength and modulus is decreasing. So at around 60 degrees Celsius, we are still around 60 to 80%. At 100, it goes around 40% and less, while at around 150, we're down to 14 to 18% of the compression modulus and compression strength of the original part. But the important message is if we temper the product at 3 weeks elevated temperature, continuously 150, then cool it down to room temperature again, we tested it, and basically the mechanical properties are completely comparable to what I showed you in the graph on the mechanical properties before. So we see that after cooling down, the continuous exposure to the temperature didn't harm the structural part integrity. So we can basically say it's really fit for purpose to serve at high temperatures. Yes, so moving on. I think we want to speak on the applications and recycling, and I will hand back to my colleague Sven, introducing you a little bit about what can you do. So you have your part now and it comes to your life end time, and now you have the question, can I recycle it? And especially in the context, there's a coating around the material, how does this impact the recyclability? And we want to demonstrate this now to you.
Okay, so as said, we wanted to study how our PET foams can be recycled. So for our ArmaPET struct PET foam, we already know that we can recycle it again in our processes. And now we also studied how to recycle the ArmaPET shape, both the P and the coated H grade. In the first step, all the materials were grinded to get a kind of granular material that could be used for molding of specimen in different shapes to do some assessment of the mechanical properties. What we tested here, it was tensile testing, 3-point bending, and also the Charpy impact test. And as you can see from the pictures, we found that there was improved ductility of the shape product. So especially for the shape H that you see in the third column, you see that there was no breakage in the 3-point bending test. And we also observed higher toughness of this material, and so it absorbs a high impact energy and has a very good impact strength. In the next step, we also wanted to study the further processing, upcycling of such material. So using the thermoprime process that we studied together with Setim Grand Est here, which is a thermomechanical process to recycle production scraps and other post-use materials. So by calendering the material, it was possible to produce a homogeneous film. And for example, such films can then be used to make a fiber and thermoplastic assembly. In this case, we studied 2 different setups. So one, the type 1 was a kind of ABA structure of the recycled shape H film and glass fiber mat. And the second setup was also using the ground RPET shape pellets in the middle of the layout. And this, those combinations were then consolidated into such kind of sheet material. And here we also prepared the samples for testing, testing the tensile in different directions of the glass fiber layup, testing 3-point bending, and also a thermal analysis. We observed decent mechanical properties with a negligible anisotropy, and also there was a good bonding strength between the fibers and the PET without any coupling agents or other additives. And also there was a limited number of voids and a good level of crystallinity. And such material is then also useful for additional processes like thermal stamping. As you can see here, we made this thermal stamping 3D parts, and this could be done despite the material had already seen several thermal processing cycles before. And as mentioned, there was also no need for further coupling agents or reactive additives in this upcycling process.
Sven, I have a question for you on this. Can the parts also be recycled into new beads again?
Well, I would say in theory, yes, if the parts will be very pure, and in this case, this would only be feasible for the non-coated grade. I think in reality, it will be quite challenging to collect sufficient amounts of this material in the purity that we need for our specific foaming process. But as we studied in this recycling case study, there are other processes that can be used for upcycling of material, and yeah, we think that is a very good example how to make new parts even out of this final molded parts that might also have, for example, some polyester skin. And if it's a polyester skin, then also the skin material could potentially be recycled in the same step.
Okay, thank you, Sven.
Okay, and now Nadine will go on.
Yes, I think from my perspective, at least, I find it quite, positive, and I'm happy that we could demonstrate in this case study that we can give this even a third life. So it's already coming from recycled materials, and after use phase, you can recycle and actually even upcycle it again into something new. And this really goes along with our vision of a circular economy when we speak about plastic products. So in this context, I wanted to show you the slide about different applications and also like kind of some buzzwords on when you hear them, when you can think about ArmaPET Shape as a product to use for actually your solution that you need. And starting with you need something recyclable or having a recycled plastic are two main buzzwords, which we hear also a lot in the especially automotive and transport industry, where this is becoming more and more important. But we also know that in a lot of different markets, this trend is really key. And I think we all know we just have one planet and we want to become more circular to reuse the materials we already have in the system. So ArmaPET Shape can be used on many markets. Actually, the slide shows you we can go into the wind business where we speak about more specific 3D parts. Of course, we don't do a blade from it because you don't want to use the shape for straight, big parts which don't have any complex shapes. There, it's not really the best solution. But as soon as it comes to a bit more complex, you have some rounds, some 3D ones where you don't want to mill specifically to lose a lot of material. There, you can also do it in the wind, in BNC. We have, for example, you see the left picture there where it's some metal frame around and then kind of a pipe inside. You can imagine this is nice for cable cannons. You can use it for beams on some specific BNC projects. In the transport and train and automotive, I spoke about that. General industry also going along with buoyancy projects where we have underwater, because this is a fused product, so it has also no anisotropy in this context. And for what kind of applications you use it then? Yes, as said, recycled and recyclable is key here, but also where you really want to focus into having something 3D waste-free. Also when it should be strong, because you saw we're not offering 10, 20, 30 gram per liter density. But for those parts that have to maintain a certain structural stability, that should be strong, withstand the temperature, and still be lightweight, there you can use it. When you want to put inserts in, like screws, cannels for something, metal parts, or have skins immediately already included in the molding step, or then have a high temperature resistance in this context. So all there, we want to give this to you as a brainstorming slide to see where in your application can you actually think about using this as a new innovative technology, having a recycled material. In this context, if we move to the next few slides, just saying we have also compiled the main information from this presentation in our brand new brochure for the ArmaPET Shape, which is available on our website. So basically, if we go through, you see that it also gives a slight insight in the molding methods and the properties that we presented, the temperature resistance. As mentioned, the Shape H is in the final industrialization, and we are super happy to collaborate with you. If you have any interest in working with our particle foam, please contact us directly and we will review your applications, give you guidance. We also have some more detailed processing guidelines that we can share on request. But we are also very happy to work together on the development step with you together to really make this work for your solution. Yes, so this is the data sheet. You find it on our website. I think we can post the link in the end of this webinar here as well. And actually, it's quite easy. Just type in Google ArmaPET Armacell or ArmaPET Shape, and you will find it in this context. So I think then we are already done with the part of the presentation, and we are moving to the final slide about questions and discussions. And I think, Benjamin, you will take it up from here.
Thank you very much, Nadine and Sven, for this great presentation. So yes, it's now time to open the floor to question, and I see that we already have a few in the question tab. So thanks very much for those questions, and thanks Sven and Nadine for starting to answer some of them. So let's start with the first question from Miles Dyson, who is asking, what is the minimum time of expansion? For example, 6 times expansion in 5 minutes.
I think I will take it up. I'm not sure if I understood it fully correct. So in theory, the time that is needed for expansion, it pretty much depends on the temperature. So as you have seen with the infrared heating, it can be as fast as some seconds in the infrared oven. When you just put it into a convection oven at 180 degrees C, then maybe the final expansion you will achieve after some 20 minutes. So it really depends on how fast you can get the heat into the beads. If the 6 times here is referring to the factor of expansion, then this factor depends on how much you would like to go down with density and from which density you start.
Thank you, Sven. I hope Miles it answer your question. Don't hesitate to ask another one if it's not clear. Moving to the next one from Pratik Rain, who is asking, what is the approximate cycle time for molding process?
Well, it's a good question because this is something which is relevant for anyone who would like to make parts. I have to say it depends really on the molding process and the part thickness. Maybe to give some idea, some indication. So when you have a heated mold, as we have shown with the 70-degree cooling and 240-degree for heating, when you have a part around 10 to 15 millimeter thickness, then the cycle time could be in the range of like 7 minutes, because you always need some time to heat it up, and then you need some time to really get the heat in the core and to cool it down again. But difficult to give a exact number because it really depends on the process.
Thank you. The next question is from Stefan Heller, who is asking, when do a cycle production the mold will be hot? Is it an issue to refill as the bead will expand when they touch the mold, so you can maybe not put all the beads you want? Complicated question.
Yeah, it's already partially giving the answer to the question. Indeed, if the mold is too hot, it could be a challenge to fill it again. Of course, there are also like automatic filling systems using like pneumatic fillers that are also used for other particle foams. We recommend that you always have to cool down the mold partially to demold the part. And I think then at the demolding temperature or slightly below the demolding temperature, it will also be possible to fill the mold again.
Thank you, Sven. The next question is from Andrew Poynton, who is asking, do I assume the tooling is normally metal? Any thought on other materials?
Yes, it's correct. In most cases, the molding, the tooling is from metal. Where it's different, it's the RF molding, because for the radio frequency molds, at least part of the mold needs to be made from a non-conductive material, so some specific high temperature resistant plastics can be used. And in general, I think for molding, using a press, also other materials that can resist a certain temperature and the force of the press while closing it may work, but it also has to transfer, of course, the heat. So then usually metal is a good material to have fast introduction of heat or cooling it down again.
Thank you, Sven. Next question from Jussi Kakonen is asking, what is the overall molding time, as many skins are not able to withstand such high temperatures for a long time?
Yes, so in this case, when you use the ArmaPET Shape H with the coating, it is possible to mold the beads already at lower temperatures, so like 180 degrees C, and then the overall molding time, it will depend again on how fast you can get the heat into the core to have the full fusion. So I think if the skin is not able to withstand the high temperature, of course, obviously it's also difficult because you have to somehow heat it through the skin. So there will be a certain limit, but especially with the coated grade, you have the possibility to go further down with the temperature. So you can see in the curing graph that you can, for example, also cure it at lower temperatures, but then you require a longer cycle time.
Thanks. Moving to the next question from Andrew Poynton again. Can you comment on processing times, including heating, cooling, and demolding?
Yeah, well, I think we have already answered this, so it really depends on the method.
Let's move to the next one then. From Stefanele, can we pre-mold to have a smaller shape, then put it in another mold with different material, then recure and continue expansion two-stage to avoid read-through on special case?
Okay. I don't know how you understand this, the two-stage to avoid read-through on special case. I think I can just answer that in theory, it should be possible to have this kind of two-step process. Of course, then it needs to be studied individually if there is still a certain expansion in the second step. I think the challenge here will be to have some integrity of the smaller part. Maybe you can mold it at a lower temperature for a short time to have some pre-curing, and then there could also be some further expansion if you go to a higher temperature in the second step.
Thank you, Sven. The next question from Jussi Kakonen. How critical these beads are for moisture? Do they need to be kept dry? Maybe Nadine can answer this one?
Yes, sure. So especially on the shape H, as we have these coating around, we recommend to store them definitely indoors and also in standard relative humidity. So if we have a high level of moisture, this can impact the surface functionalization. So these beads have to be stored at room temperature and standard humidity level. So if it goes too high, this can be critical, especially there. For the pure beads is not as much of a concern, but still also here we recommend to not store in very humid or hot conditions.
Thank you, Nadine. Next question from Pratik Rain. Can you elaborate on yellowing tendency of these particles while processing at high melt temperatures?
Okay, so normally if you work with the recommended processing temperatures, then there's normally no yellowing of the material. As you have seen, normally our material is greenish, which is also maybe less critical for yellowing than the white material. Yes, but of course, if you exceed really the temperatures, or you are close to the melting point for much too long time, then there could also be some degradation or yellowing of the material.
Thank you. Let's take some last questions. Samuel Lafranchini is asking, how high is the thermal count in comparison to standard PET foams?
Okay, I think this is referring to thermal conductivity of the parts. There we did some testing on reference samples, and depending on the density and the molding method, we are more or less in a similar range than our standard PET foams. Maybe it will, if there's a certain requirement for thermal conductivity, then it needs to be tested individually for really the part and thickness and density.
Next question from Michel Champagne, who is asking, how would you recycle those foam metal hybrids?
Okay, so actually I didn't think of recycling the foam metal hybrids yet. I know there are quite some projects going on also on recycling hybrid materials. I can imagine there are some mechanical processes that can be used to kind of break down those materials so that you can, for example, separate the metal from the PET again. So I think that I would recommend to go in this direction.
Thank you, Sven. We're running out of time, so let's take a last question from Leo Reiner, who is asking, what's the thermal expansion after the foam has cured?
So I think it's this is referring to the linear thermal expansion of the final foam. So we haven't measured this yet for our bead foam, and again it will also depend on the molding method and the part geometry.
Thank you very much, Sven and Nadine. The event has now come to the end. I would like to thank everyone for joining us today, and thanks for all your questions. Don't hesitate to get in touch with Nadine and Sven if you have any more questions. You have their details on screen. We hope that you enjoyed the time with us today and that you learn more about ArmaPET. I want to thank Nadine, Sven, and all team involved at Armacell for this webinar today. Thank you very much. The webinar was recorded and the link will be sent to you immediately if you want to watch it again, and it will be also available on JEC Group Web TV at geccomposites.tv, where you can access to all previous webinars, exclusive video contents, and conferences of JEC Group events. We look forward to welcoming you during our next event on November 23 and 24th at JEC Forum DAR in Frankfurt. I know that Armacell will be exhibiting, and I think Nadine will be in the attendance. So don't hesitate if you want to meet Nadine, Armacell, and the 60 plus other exhibitors coming to Frankfurt in November. You can get more information by visiting gec-dar.events. Thank you very much again, and I hope to see you again soon in Frankfurt or online again for our next webinar. Thank you. Bye-bye.
Thank you, Benjamin.
Thank you. Thank you very much.